what we found was that at a pressure of 10 to the power minus 2 mm of Hg, and when a potential difference of 10,000 to 15,000 volt was applied between these two electrodes, then the luminous glow was seen on the wall, but not inside the discharge tube. Okay, the glow was seen, but the glow was seen on the wall of the discharge tube, not inside the discharge tube. All the glow that appeared inside the discharge tube vanished. Okay, and they were negative glow and cathode glow. So negative glow and cathode glow vanished, and then only one glow was seen on the screen, and that glow. Wait for timing. Okay.
David Kaple.
Okay, sorry, students. So a glow was seen on the wall of this discharge tube, and then what scientists at the time thought was that if there is a glow on the wall of the discharge tube, then this has to be because of some invisible rays. Okay, this has to be because of some invisible rays. And in a further to study about the nature of this invisible ray, J.J. Thomson used Crookes dark space, okay, where he used a Malthus cross here. So this is a Malthus cross. So with this Malthus cross on Crookes discharge tube, he further studied the properties of the invisible ray. Okay, so what he found was that when when it was connected to a high potential difference, and the invisible rays start coming from this cathode plate, and it went towards the anode plate, right? And then when the invisible rays originating from the cathode plate was had an obstacle or had an encounter with the Malthus cross, then what he found was that there was a shadow casted on the wall of this screen, on the wall of this discharge tube. Okay, and this Crookes discharge tube. So it's a special type of discharge tube used by J.J. Thomson to study more on the properties of the cathode rays. Okay, so what happened here is that when there is a Malthus cross in between this cathode ray, or in between the cathode and the wall of the discharge tube, then what he found was that there is a shadow. So here is a shadow of the Malthus cross here, and similarly here on the wall of the discharge tube there was a glow. Okay, and then from these two properties, what they found is that there has to be an invisible rays. Okay, and then they were still in doubt whether that invisible ray has to be called as wave or as particles, or they were trying to figure it out whether this invisible ray is wave, just like the light ray that we receive from the sun, or is it the collection of particles. Okay, so in order to further study that one, in order to find out whether it's a wave or a collection of particles, then J.J. Thomson studied this property. Okay, so here is the discharge tube with fluorescent screen, and then see here the ray is coming out from this cathode. This one is cathode here, from cathode, and it's moving towards the anode. Okay, now when this ray is being considered under the influence of magnetic field, or if you bring a magnetic field near to this ray, then what you obtain is, okay, see here, so it is being deflected. Okay, so it's being deflected. What we saw was that the ray is being deflected on the downward direction, as you can see it over here. So if the invisible ray is deflected, okay, here it seems just like visible because of the fluorescent screen. So it's deflected downward. It means that these ray or these invisible rays are the collection of the charged particles. Okay, and then further, what they found was that when they place that ray in magnetic field, when they place that ray in the magnetic field, this was the deflection, right? So it is a charged particle, And when they place that ray, okay, when they place that ray in electric field, then that ray was deflected towards the positive terminal. So it says that it's a particle, this being deflected in the magnetic field, and then as it is deflected on the upper plate, when the upper plate is provided with positively charged terminal, is connected to positively charged terminal, then see here, if it is connected or if it is attracted towards the positively charged plate, then only the dissimilar charges get attracted. So from the magnetic field deflection, they found that it's a particle, and by applying the electric field, and as this ray deflected towards the positively charged plate, they found that it has got a negative charge. Okay, so finally what they found was that this invisible ray, okay, is a collection of particles which is negative in nature, okay, or it is a collection of negatively charged particle. In the beginning, in that time, electron was not, or they did not name it as an electron, right? They named it as a corpuscle or as a particle, and later on they named it as an electron. Okay, so J.J. Thomson found that this stream of this invisible ray that is being emitted from this cathode and reaching the anode, this invisible ray is actually the stream of corpuscles or particles, okay, which has negative charge, or these particles are the charge carriers and they carry the negative charge. Okay, so finally J.J. Thomson discovered that these cathode rays are the invisible rays that are made of a stream of negatively charged particles, which we call now as electron. Okay, so this was how J.J. Thomson discovered electron, by doing research on the cathode ray. So he did a research on this cathode ray with the help of his instrument. Okay, his instrument, as well as he used the Crookes dark space as well. So here you can find out his instrument. He used this instrument, okay, and using this instrument and then using these properties just like a Maltese cross, okay, and fluorescent screen, this fluorescent screen, what he found was that it is made up of particles, and these particles are negatively charged. And in further nowadays they exploited the property of this cathode ray, and they were much more confident that the rays are not waves but they are particles. Okay, as you can see over here, here's a paddle wheel. So see here, and this is cathode. Okay, so the ray is coming out of this cathode, and as the ray is coming out of this cathode, if it moves this paddle wheel, then this ray will have the energy. Okay, if ray has the energy, then energy is related to the momentum. So if it has got the momentum, then it will strongly advocate that it's particle in nature. Okay, as you can see in this video. Okay, let us see here. Now this is the paddle. Now see here, it's moving here, right? It's moving. So as it is moving, so see here, the paddle wheel was here, and then when a potential difference was applied, then the cathode rays start emanating from this cathode plate, and then it started moving this paddle wheel. So if it moves the paddle wheel, it will move only if it has got the energy. If it has got the energy, then obviously it will have the momentum, right? If it has the momentum, then it strongly advocates that it is particle in nature. Okay, so this was how J.J. Thomson discovered from the research of cathode ray that cathode ray is made up of stream of particles known as electrons. So this was how the electron was ultimately discovered by J.J. Thomson, for which he got the Nobel Prize. Okay, so after discovering the electron, so let us congratulate. Okay, these around 4 or 5 lectures were just we spent those lectures in order to find out how J.J. Thomson discovered the electron, and finally we discovered it. Now after this one, now we'll study different properties of electron. Okay, and it is included in our chapter number 1. So first and foremost, we'll be studying this property, the property that we have already discussed, but we haven't explained why it is happening so, right? This property when the electron is placed inside this electric field set up by these 2 plates, okay, one positively charged and another negatively charged. So we'll be studying in the beginning this one, what happens when an electron is placed inside an electric field set up by two metallic plates in which one is positively charged and the other is negatively charged. So this property today we'll be dealing, and for this one I've got the worksheet, and the same worksheet I forwarded it to you. I don't know how many of you have ever gone, if you went through this or not. Okay, it would have been very beneficial if you had gone through this one. And then the second, in the upcoming lectures, we'll be discussing the property of electron in the magnetic field. Okay, so first and foremost, we'll be studying in the electric field, then in the magnetic field. Then when both electric and magnetic field is applied simultaneously, okay, or at the same time. Here it has been studied separately here. Once in electric field and second in magnetic field. Now the third event that we'll be studying is while both these electric and magnetic field are placed. At that scenario, what happens? Okay, and then after that one, we shall derive an expression for the quantization of charge. This way we will finish our chapter. So I think it may take, if we went smoothly and if there is any disturbance, I think we may finish within 2 weeks. Okay, this first chapter. And then I've been regularly sending you the videos, go through it, so that it will be very much beneficial. If you can't, or if you are finding problem while I'm teaching you online, okay, so you can go through those videos. And this also, I'll be sending it to you. I think it's recorded, right? Yeah, it's recorded. I'll be sending it to you later on. Now, let us go on to that one. Okay, what happens when an electron is placed in an electric field set up by two plates which are oppositely charged? Okay, for this one, I have got this simulation. Okay, so one of you, please cooperate with me, unmute yourself, and which charge do we find on the upper plate here? Please tell me, one of you. Which charge do you see here on the upper plate? Hello?
Positive.
Yeah, positively charged. Thank you. Who is this? Rides? Is it Rides? Or
Yes, sir.
Pradin? Is it? Okay, okay. Thank you. Okay. Similarly, cooperate in that way. Okay.
सर बोलाउनु
So that,
भएको भर्खरै
होइन, तिमीले भने जस्तो लाग्यो यसको आन्सर हो कि कसले भनेको थियो?
खै सर
Okay, fine. Just leave it. Okay, but please
Sir,
cooperate with me. Okay, please cooperate with me. Okay, and then what sort of charge is over here? This one. Tell me. See, which charge is here on the lower plate? Hurry up. Look,
Negative.
Negative. Yeah, hurry up. Okay, so that I can continue my class. So see, the upper plate is positive, the lower plate is negative. And as we have already studied in capacitor, if there are two plates which are oppositely charged and then placed at a certain distance or certain separation d, so if this upper plate and lower plate is separated by a distance d, and then the upper plate is provided with positive charge and the lower plate is provided with negative charge by applying a voltage, okay, by applying a voltage capital V, then the electric field will be set up from positive to negative. See here, all these are the electric field lines, and the value of this electric field equals to capital V upon D, where V is the voltage applied and D is the separation between these two plates. Okay, now in this scenario, what happens if we put an electric field, or if we insert an electric field, or if we fire an electric field inside this region set up, or inside this electric field region, okay, set up by these two parallel plates. Let us see here now, for a nice trajectory. Okay, first let me shoot it. See here, what's happening? This electron is moving towards the positively charged plate. That means this electron has got negative charge. That's why it is moving towards the positively charged plate. If here was the proton, then what would have happened here? Okay, let us see here. So see here, proton is being deflected towards the negatively charged plate. Okay, so from this simulation, now I would like to come onto our worksheet. So was it here? Yes. I think you are seeing this worksheet, right? Is it visible for everyone here? Are you able to see this worksheet? Motion of electron in an electric field?
Yes, sir.
Okay, so see here. So here the electric field starts from positively charged plate towards a negatively charged plate. So it's going in this form, right? See here. Now I would like to ask one of you. Please do not leave the classroom, okay? So let me ask Kaushal, okay? Kaushal, unmute yourself.
हजुर सर
यहाँनिर नि यो क्वेसनको एन्सर भन त यसमा मलाई खालि के भन्दा नि अपर पोजिटिभली चार्ज प्लेट कि नेगेटिभली चार्ज प्लेट मात्रै भन ल है यो एन्सर इन विच डिरेक्सन वुड डिरेक्सन नभन हैन अथवा इट मुभ्स टुवर्ड्स नेगेटिभली चार्ज प्लेट भन्न नेगेटिभली चार्ज प्लेट भन्न अथवा पोजिटिभली चार्ज प्लेट भने पोजिटिभली चार्ज भन्न अथवा यसलाई ईस्ट डिरेक्सन मान यो नेगेटिभली चार्ज प्लेटलाई ईस्ट डिरेक्सन मान अनि पोजिटिभली चार्ज प्लेटलाई वेस्ट डिरेक्सन मानेर इसका आंसर गर था in which direction would a proton positive charge accelerate in this electric field
टुवर्ड्स द ईस्ट किनभने त त्यो एरो हेडतिर जान्छ नि त
ओके किनभने यो नेगेटिभली चार्ज प्लेटतिर जान्छ ओके न पोजिटिभ चार्ज नेगेटिभली चार्ज प्लेटतिर जान्छ सो टुवर्ड्स ईस्ट or towards the negative charge. Thank you so much. Now the next one, thank you Kaushal. So Srinal, unmute yourself. Srinal, are you listening to me? Okay. So answer this question, the second question. In which direction would an electron accelerate in this electric field? In which direction? कतातिर जान्छ होला यो? Another? Towards the positively charged plate or towards the negatively charged plate? Srinal, electron. Hurry up, please. Do not waste our time, class time, okay? Hurry up, Srinal.
उसको माइक बिग्रिसक्यो अरे
तेरीका अनि यो को बोलिरहेछ यो बोले जस्तो श्रीनल बोले जस्तो लाग्यो मलाई ल ठिकै छ सुप्रिया अनम्यूट योरसेल्फ सुप्रिया
Yes, sir.
okay now tell me in which direction would an electron accelerate in this electric field? Does it move towards positively charged plate or towards negatively charged plate?
Positive.
Yeah, towards positively charged plate, right? As it is evident from this one. So see here, if it is electron, then electron will be moving towards the positively charged plate. And if it is the proton will be moving towards the negatively charged plate, okay? Now let me decrease this electric field and then see what happens, okay? What happens, only little amount. Now see here, only few or for this nice trajectory, I have done this one. Now see here, what happens while we fire an electron, okay? What happens while we fire an electron inside this electric field? Or how does the electron move in an electric field set up by two oppositely charged plates? Okay, let us see here. If we see it here, then what we see, it is being deflected. What is it being deflected? It is being deflected towards the positively charged plate, okay? So in today's lecture, what we are going to do is, suppose this is the point P. Now see here, I think you are seeing the arrow, okay? Suppose if this is the point P, where the electron reaches in the time interval t, small t, okay? It takes the time interval t from reaching here to here at this point that you have taken. Now today's lecture will be focused on what will be the x component of, or this point can be represented as pxy, right? So we are trying to find out what is the value of x and what is the value of y, okay? So today's lecture will be focused on that one. And if we can finish that one, then we shall continue on it. But let us try to finish what is the value of x coordinate and y coordinate at this point P when an electron reaches in the time interval t, small t, okay? Now, for this one, now let us see here, okay? So see here, in order to or how we shall study the motion of electron in an electric field, and it's very important for numerical problems. Really, it has been asked in the long question, okay, as a long mark question, but it has been frequently asked in the numerical problem. So we need to have the concept, okay? So we'll approach this first step today, first and second step. Then third and fourth step we'll be leaving for tomorrow's lecture, okay, or upcoming lecture. So how will we explore this topic, okay, motion of electron in an electric field? First and foremost, we'll be drawing the figure of the experimental setup. So this is the experimental setup. So this experimental setup will be drawing the figure, and I think everyone is there with copy and pen, right, or pencil. And then the upper plate is positively charged and the lower plate is negatively charged. So just like here, we shall be drawing this experimental setup where the upper plate is positively charged and the lower plate is negatively charged. Then after that, an electron beam is launched with the initial horizontal velocity v, and the electron deflects in a parabolic trajectory towards the positively charged plate. So here, as you can see over here, this electron is here is shoot, okay, or is made to, or here we are taking the horizontal velocity of the electron to be v, and as it approaches this electric field with the horizontal velocity v, then how is it moving? Okay, so here it's moving in a parabolic form, yes or no? So we have observed this one. Now we'll have the power of mathematics and we'll find out the expression or the mathematical expression representing the parabola, and obviously that is the second order equation, yes or no? So second degree equation always represent a parabola, yes or no? And first degree equation represent a straight line. So we'll be seeing the power of mathematics, okay? We'll find out the mathematical expression or the equation in second degree, which will prove that this trajectory is, of course, parabolic in nature, okay? So we'll be seeing up to there. I think we can finish only up to there. And then after that one, we'll be finding the horizontal displacement x and the vertical displacement y. By that, what I mean to say is that we'll find out any point, or we'll take any point. Let us suppose we are taking this point P, and it's given by the coordinate x and y. So we'll be finding out the value of x and we'll be finding out the value of y, okay? So this way we'll be exploring our chapter today. If you have printed out this one, that's very good. Now you'll be writing here itself. If you have not printed, then bring copy and pen, okay? Hurry up, and then we'll start doing it, okay? So summary. Now I'm going through this worksheet. So this will be a note for you as well, okay? And after this second lecture, or after we complete this one, you have to submit this PDF file to me as an assignment. An electric field is set up between two opposite charge plates. Here we have set up an electric field between two opposite charge plates. When an electron enters an electric field set up in between these two opposite charge plates, it deflects towards the positively charged plate. That's the summary, okay? So an electric field is set up by these two opposite charge plates, and when an electron is projected here, or let us not say projected, okay, when an electron is fired here, or when an electron is made to move inside this electric field, then the electron is attracted towards the positively charged plate. That's the summary, okay? Now for that one, now here the worksheet says that with the summary and the concept provided above, draw the experimental setup for the motion of an electron launched with the horizontal velocity v between two oppositely charged plates. Upper plate is positively charged and the lower plate grounded by applying battery of voltage v. The length of the horizontal plate is d and is separated by a distance d. Now you'll be drawing with me, okay? So let us start drawing here. So what it says is that, so I think you are there with, pencil and copy, right? So let us draw it, okay? So we are drawing. So here are two charge plates, okay? So this is one metallic plate and this one is the next metallic plate. And what we are doing here is we are applying a potential here, okay? A potential here. This one being positive terminal, okay, or having higher potential shown by the longer length. This we connect it here in the upper plate. So if we connect this on the upper plate, this will be positively charged. And then I think you are drawing along with me, right? Are you or not? Let me see how many of us are here. 27, good. Are you drawing along with me?
Yes, sir.
Yes, thank you. Just draw along with me, okay? And later on, you have to fill up that PDF file and then send it to me for correction. So we'll be following that PDF only. So see here. So this one is having the higher potential, and this one is connected to the lower plate. So this one is negatively charged, okay, or it's connected to the lower potential. So this one is positively charged. Draw along with me, but draw nicely, okay? Here I cannot draw it nicely. It's becoming irregular here. Positive charge itself is becoming irregular, but draw it nicely, okay? So here you'd write nicely. This upper plate is positively charged, and this lower plate is just below. Okay, draw negative charge here. Negative charge, negative charge, negative charge, negative charge, negative charge, negative charge, negative charge. Now here is positive, here is negative. So electric field will be set up from positive to negative. Okay, in this way. So this is the electric field that's being set up here. Here, this is the electric field, and again this is the electric field. Okay, so we are setting up the electric field here. So set up everyone, right? Nicely, but okay, straightly use this skill if you have got this skill. So this is the electric field, and then the electric field is originating from positively charged plates and it's going to the negatively charged plates. See the direction, okay? Electric field is a vector quantity, so it has to have the direction. Now here, we are applying a voltage V here, okay? We apply a voltage V, and these plates are separated by a distance d. So if these plates are separated by a distance d, so this is our distance between these two charged plates. This is our distance, okay? And it is separated by a distance d. Then an electric field will be set up here, and that electric field is given by E. Okay, so now here, if the electric field is E, potential is V, and separation between these two plates is D. Now I'm going to ask one of you, Susrap, please unmute yourself. What is the relation between E, V, and D? Tell me, what's the relation between E, V, and D? What's the relation between E, V, and D? Unmute yourself, Susrap, and then tell me. Hurry up, please. Okay, this way I think you won't be answering me. Okay, from tomorrow I won't ever take your name. Okay, Suyok, unmute yourself and then tell me what's the relation between E, V, and D, electric field setup between the two charged plates where V has been applied, and D is the separation between these two. So what's the next one? Suyok? Okay, Swati,
Azur sir.
Lavanatha, what's the relation between E, V, and D? Hurry up. What's the relation between this E, V, and D? Tell me.
E is directly proportional to V and
E is
inversely
directly
proportional
proportional to V, very good, and inversely proportional to
D.
D, yes, very good. Or we can say that here what you can say equals to E equals to capital V upon D. Sorry, D. You also go on writing it, okay, this expression. Where is the electric field? V is the voltage, okay, or the potential difference applied between these two parallel plates, and D is the separation between these two parallel plates, okay. So what happens now is, now this is our one of the relation. Okay, now what we are going to do here is, we are going to fire an electron here. We are going to fire an electron here, just like we have done here. We are firing an electron. So as we shoot an electron, what happens? It gets deflected. Yes or no? Here also we are trying. We are doing the same thing. Okay. For a clarity, let me erase this one, electric field. Now I think you know here is an electric field. So now what we have got is an electron. Now an electron is fired from here with horizontal velocity v. See here, this is a small v. Okay, with a small v, we are firing an electron. So if we fire an electron here, up to here it comes in a straight path. Okay, this one is a straight path. Let me try to draw it. So see here, from here to here, okay. See here, we are facing huge problem, right, teachers? Okay, now see here. So this is a straight path, let us suppose, okay, in physics we can suppose, and it's a straight path. Now here is the electric field here inside this region. Here is no any electric field. So as here is no electric field, electron doesn't get deflected here, okay. Now right after, or just as it enters this electric field, then it starts getting deflected, okay, and it starts getting deflected from here, then it goes in this way. So it's being deflected, just like this one, okay. Here the electron is being deflected, and similarly here I projected this electron with a horizontal v such that it just emerges from this upper plate, okay. Here it could not emerge because here the velocity was lesser, and as the velocity is lesser, here it was not emerged, okay, or it did not emerge from this plate. It was attracted here, okay, but here I put enough velocity so that it just emerges from this upper plate here, okay. And now here, Here, what happens? Now, again, here the electron doesn't get any electric field. So I think you have studied in this one, right? Mechanics, classical physics, that when certain object is swirled or rotated in the circle or in the circular motion, and then if it is really suddenly, then it moves tangentially, right? The same phenomena will be observed here, okay? As it comes out from here, luckily it's also tangential, it goes tangentially. So here, from here, it goes tangentially, okay, in this way, tangentially. And this is the velocity now. Now, let us see how far we have done from the worksheet. So we did this one, okay? We have applied the voltage V, and then with the horizontal velocity V also, we projected it, right, or launched it. The length of the horizontal plate is D and is separated by a distance D. Okay, now here, what does it mean is that the length, this horizontal length, and these are two equally, or they have got two equal lengths, okay, horizontal lengths. So the length from here to here is equal to the length from here to here, and it is capital T. So see here, the length of this plate is capital D, and the separation is small d. I think you are getting it, right? The separation is small d, and the length of this plate is our capital T. Okay. Now here, and then here it is moving tangentially. Now let us further go to the worksheet. Now listen, okay. As the electron enters the electric field, it starts deflecting towards the positively charged plate in a parabolic trajectory due to the electrostatic force F equals to EE. Now let us see here. So here, as soon as this electron reach here, so the electron is reaching here. As soon as this electron reach here, it is influenced by the electrical force, and the electrical force will be always towards this positively charged. So here, this is electron, so it will be moving towards the positively charged plate. Okay. Now we are asked to find out the electrical or electrostatic force between these two plates, and we know that. Wait. Okay. Let's say. Okay. Now what we know is here, this electron reaching here, okay, the electron reaching here, here will experience the electrostatic force, and that force is given by F equals to Q capital E, where Q is the charge of the electron or charged particle, and E is the electric field. Here we are studying the motion of the electron, so this can simply be written as F equals to EE. As you know that E is the charge of the electron. Yes or no? So I think that you have written up to here. Then further, now here, substitute this value E equals to V by D here. Then what you can find out is the electrostatic force being experienced by that electron equals to E, and then capital V upon D. So let us write down this one as expression number 1. Okay. I think you got up to here. Did you get here? Everyone, are you writing the same way that I am writing here? Oh my God, I deleted it. Sorry. Let me write down again. So F equals to QE, and then Q equals to E. Therefore, F equals to EE. Also, as you know that E equals to V by D, F equals to E V upon D. Okay. So that was what we studied. Now, so let us place it over here, or let me place it over here. Okay. Now here, after that one, what does it say? Do you have any question? You can ask me. If you have any doubt up to here, you can ask me. Do you have got any doubt up to here? Anyone? Or shall I start? Or shall I continue? I mean to say. Any question? Okay, now after that, then what happens here? Here, where is the electronic charge and is the electric field given by the relation E equals to V by D? We have already written this one. V being the voltage supplied between two plates with a separation of distance D. Now assume any point Pxy in the trajectory. Okay, now let us assume any point Pxy in the trajectory. So let us take this point. So see here, this is our point, and this point is has got the coordinate. The point is P, and it has got the coordinate x comma y. Okay, so here x comma y. Now here, So this is the displacement. Yes or no? This is the displacement. If you consider this one as the initial position and this one to be the final position, then this distance covered or this displacement can be categorized into two components, or it can be split into two components, just like here. Here, suppose this is the vector A, and vector A, suppose this is the displacement, okay, it's a vector quantity. So what I can do is that I can resolve it into two components, yes or no, along the x direction and along the y direction. Similarly here, this displacement from here to here, this displacement from here to here, though it's not in a straight path, okay, we can draw a straight line from here to here and we can assume it to be S, okay. So this displacement S is divided into two components along x and along y. So let me take two pencils here. So this is the resolution of that displacement vector along the x component and this one along the y component. Or what I mean to say is that this one is x here, this one from here to here is x coordinate, and from here to here is y, okay. Now one of you please tell me what's the relation relating S, U, A, and T. Hurry up, okay? What's the relation relating S, U, A, and T? Any one of you, please tell me. Whoever wants to tell, please tell me. Hurry up. What's the relation between displacement, initial velocity, acceleration, and time? Please cooperate with me, okay? Look. Oh my God, I have to ask you individually. Okay, okay. Swati, what's the relation between displacement, initial velocity, acceleration, and time? Swati, am I listened? Are you listening to me, Swati?
S equals to half ut square, sir.
S equals to half ut square? Is it? S equals to half? What you're saying? S equals to half
ut plus half at square.
Okay, so in that, tell in that way. Thank you. S equals to ut plus half at square. So here, if we draw a straight line from here to here and assume it to be S, then S equals to ut plus half at square. Okay. Then here we are dividing this one into two components. This S into two components. One is along the horizontal component, that is known as X. Another is along the vertical component, that is known as Y. Okay, so here this displacement is divided into two components. One is along the horizontal component X and another is along the vertical component Y. Now this is somehow related to the projectile motion, okay, but fundamentally we cannot say that it's a projectile motion, because for any object to be in a projectile motion, it has to be attracted to 15. So here, this is the projectile motion, yes or no? And I am just launching it with an initial speed of 15 meters per second. So this is the projectile motion. Why? Because only one force is being exerted, and that force is towards the ground, or this is due to the force due to gravity. Here, somehow we can relate it, but we cannot tell it as a projectile motion, because it's not the force. Only one force is being exerted here, but that force is because of electrical force, not due to the force due to its weight. Okay, so if an object is not moving under the influence of the force due to its weight, we cannot call it to be a projectile motion, but somehow it can be related. See, it is going down, it is going down, okay, it is going down here, and it has been launched with the initial speed of 15 meters per second. Here it's going up, okay, and it has been launched with the initial speed of b meter per second. And then see here the force due to gravity is negligible, because the mass of the electron is very small. Yes, it's negligible, as the mass of the electron is negligible. Mass multiplied by acceleration due to gravity is also negligible. So force due to gravity is neglected over here. So only one force is being exerted here, and that force is due to electrostatic force, and this negatively charged electron being attracted to the positively charged plate. Hence, one electrostatic force is being exerted on this electron and towards the upper plate. Okay, So now see here. Now what we need here is this x. Now what will be the initial velocity of this x? Tell me, one of you. By how much horizontal velocity have we launched it? We have launched it with the velocity v. Yes or no? So here the initial horizontal component will be v, and let us suppose the time taken to reach at this point is t, so it will be vt. So this is the expression, x equals to vt. Now why won't here be an acceleration? Okay, let me ask one of you. Okay, here I have removed acceleration. Why do you think I have removed acceleration? So this question goes to Pramithas. Are you there, Pramithas? Okay, Pramithas, why do you think here the acceleration equals to 0 along this horizontal displacement? Tell me.
Because there is no force, and since there is no force, acceleration won't be produced.
Yes, very good. Only one force will be exerted, and that force is along the vertical direction. Along the horizontal direction, there is no any force. So as there is no any force, acceleration equals to 0. Thank you so much. So this was the question I have asked you here. Okay. So the horizontal displacement x equals to vt, where v is the horizontal velocity with which an electron is launched in the electric field, and t is the time taken. In the expression third, okay, here it has to be third. There is no acceleration because, as Pramita said, that there is no any horizontal force. No horizontal force means no horizontal acceleration. Okay. Now here, now the second question, let us see here. Vertical displacement y equals to half weight acceleration of the electron, and is the time taken. In the expression 4, okay, not 2. In the expression 4, there is no initial velocity because now here. Now what we are going to do here is now y will be writing as t cap 2, okay, or at square. Who can answer this question voluntarily? Please answer me. Anyone try for it? Anyone can try for this one? Why we wrote here initial velocity equals to 0? That means along the vertical displacement, initial velocity equals to 0. Why? Who can say this one? Any one of us? Do not make me repeatedly call your name, okay? Okay. Ayush Yadav, I see the reason why the initial vertical velocity equals to 0. Ayush, are you there? Ayush. Okay, Bhavana, can you try? Bhavana? Okay. Why do you think the initial vertical velocity is 0 over here?
The vertical object गर्ने बेलामा थ्रो गर्ने बेलामा चाहिँ इनिशियल त फर्स्टमा 0 नै हुन्छ नि त, अनि त्यसपछि मात्र त्यो भएर हैन
हैन के चाहिँ इनिशियल 0 हुन्छ? इनिशियल भर्टिकल भेलोसिटी चाहिँ 0 हुन्छ कि इनिशियल हरिजन्टल भेलोसिटी चाहिँ 0 हुन्छ?
भर्टिकल चाहिँ 0 हुन्छ हैन?
भर्टिकल चाहिँ 0 हुन्छ. किन होला? Because here we are see this component, okay, here, okay, let us see here. Thank you. So velocity vector सेरे हेर ल यसलाई, यसलाई velocity vector सेरे हेर, यसरी प्रोजेक्ट गर्यौ हामीले र यहाँ हेर्दाखेरि यहाँ हेर त, यसलाई हामीले हरिजन्टली लन्च गरिरहेको छ नि, भर्टिकली लन्च गरेको छैन. सो हरिजन्टली लन्च गरेको छ, भर्टिकली लन्च नगरेको कारणले गर्दा इनिशियल भर्टिकल भेलोसिटी चाहिँ 0 हुन्छ. ओके, so here you will be writing because it is launched horizontally, it's not launched vertically. Okay, or you can write down because it's launched with horizontal velocity b meter per second. Simply up to here we'll be doing today. Okay, everyone who are present, write down PPP over here so that I can take your attendance, and then after writing P you can leave the class. Thank you so much. Okay, I shall send this recorded video to you, and you once go through it and then try to do the rest of the assignments on your own as well before coming in this lecture. Okay, thank you, students.
Awesome.
Awesome.